Hello everyone, welcome to MACSMIN 2025. It's a pleasure, really pleasure to introduce Professor Aleksandr Chernatynskiy, my former classmate from school, who will talk about a symmetry-oriented crystal structure prediction method. Over to you, Alexander.
Okay, thank you very much. Thank you for the introduction and thank you for this invitation and opportunity to talk to you guys about this. I hope everybody see the presentation slide and not the picture that I have from PowerPoint on my screen. So hopefully I did it the right way. Let me first say thanks to people who were involved in this work and this project. Ji Zhang is my graduate student who successfully graduated last year. He is the one who did all the heavy lifting on this. I'm rather happy because he actually found a job which directly relates to this. He is actually working on in a startup in China on creating a new battery systems. So this was exactly our main motivation, and so I hope what he learned here was actually useful for him. Luke is an undergraduate student who started to work on this project following Chi departure. And Amitav Chatpuri is my chemist collaborator from the chemistry department here at Missouri S&T. So I guess strictly speaking, it should be physics and chemistry, with who in large part motivated this project by asking me questions. Could you tell me anything useful about the systems that I'm about to discover and so about to discuss? And so this is what we are trying to accomplish here. This was a self-sponsored project, and I also would like to acknowledge the high-performance computing here at Missouri S&T. We have a computational center which allows all of us to use and run various simulations with a relatively straightforward manner. Okay, so let me show the outline of my talk, even though maybe not super important, but nevertheless, let me first do the introduction, why we are interested in the type of the materials that we are interested in. I'm very much more coming from the physics side. I was involved a little bit with the questions which were discussed in the previous talk somewhat, but really not too much. I was thinking about this subject, but my background is really going in the direction of physics and going in the direction of materials properties, rather than a big data kind of thing. Nevertheless, I got involved in the structure prediction thing, and the first thing which pops in my mind is that that's a global optimization problem, and we really need to worry about dimensionality reduction. So I will tell you how we do this in this particular instance. I will present what the results of our method is. We so far, I think, rather successfully tested it in a couple of cases where we do know what the structures are going to be, and so this is tests rather than predictions at this point. I do have a little bit of the involvement of the big data because this is, you cannot have a talk without it right now. Finally, I will conclude. So let me start with the motivation. We are interested in these compounds, which we called complex chalcogenides, which sit in here in the middle. I very roughly put down the chemical formula for what those are. So I will say right away that whatever I'm discussing now is tailored to these particular compounds. I'm not sure how widely applicable that is. What kind of materials we're thinking of? I have something which will have a chalcogenate. So this is element Q, which is sulfur, selenium, tellurium, something on that front from that column of the periodic table. M stands for the main part of the table element. So there's something like phosphorus, silicon, germanium, gallium. That might be some going a little bit into the metallic side as well. And X is a metal, and because our main motivation comes from the solid state batteries, something like lithium batteries, then our metals are typically going to be lithium or sodium or something of that nature, or possibly a combinations of the few. It doesn't have to be only one element. These materials are starting to find various applications because they allow us expand the chemical space into various properties. And a lot of times it's maybe not even necessarily what the key property that we are using them in, say, in the nonlinear optics, how optimal they are for generating the nonlinear effects in the optical spectrum, but rather their agreement with various other constraints and requirements. So chalcogenides tends to be a little bit softer when we're talking about bulk modulus in comparison to oxides, for example. They tend to have a lower temperature that is required for their synthesis, and there is a whole bunch of other characteristics that might be more suitable in some particular applications than others. And so we are trying to kind of explore this state. As I already mentioned, solid-state batteries is one possible application. Lithium is, of course, heavily used for that, and in particular, lithium PS4, one of our test compounds, is being suggested to use as electrolyte for the solid-state batteries due to its highly efficient super-ionic conducting properties. Nonlinear optics is another example of the applications. I'm kind of citing here the particular compounds that we worked on, or maybe Dr. Chakuri worked on. Thermoelectric materials, in this case, we are interested typically in lowering thermal conductivity of the compounds while keeping everything else intact. And complex structure of these materials is very beneficial for that. So this might be very useful and promising application. They are also applied in photovoltaics and other places. A lot of times our work here is really develop the possible compounds with desired properties. And we, sitting on the fundamental side of things, we leave a job of actually using that for something to somebody else. We are really working on the fundamental side, trying to predict new and interesting compounds in this area. So the crystal structure prediction, I probably doesn't really have to tell that, but nevertheless, it is really a global optimization problem. You really can think about that as optimizing the energy of the compound as a function of positions. And depending on the number of atoms in my system, I'm going to fairly quickly hit the dimensionality curve, which is the potential volume of the configuration space is divergent very quickly with the number of atoms. So the number of degree of freedoms here is kind of a key parameters. And typically, I think if you go through the literature, if you have somewhere on the scale of 20 degrees of freedom or something, you're probably going to find a reasonable approximation to a global minimum. If you're starting to push further, then you're probably going to be out of luck. This is as applied to these solid state systems. In this particular instance, we are interested not only in stable system, but we are also interested in the metastable structures. And there is a multiple reasons for that. You never know what the kinetics is, so you don't really know if you can stabilize or not stabilize particular metastable structure. But quite often there is a situation where you will have a sequence of phases available in given material, as I discuss lithium PS4 system later on. This is particularly, for example, a situation in that scenario. At this point, we do consider fixed chemical composition in ordered crystals, and this is really something where really the frontier is and where we would really like to go, although I admit I don't really have a very clear idea how to do this. But choosing the stoichiometry of your compounds is one of the key issues, and I will touch a little bit upon them, but I discussed the rigid blocks as well. And effect of disorders is one of the key elements. Again, as I will point out in the future discussion, many of the phases that actually have interesting and promising properties do feature some degree of disorder, and that has been a challenge for the prediction part. The last but not least, it is in principle possible and should be possible, and one would not necessarily want to optimize only against energy, but also against the particular properties of interest. So you kind of want to hit two birds with one stone, I guess, rather than saying that I have all these structures possible and that they might be interesting, but let's now go ahead and figure out what kind of properties they have. One can include those properties evaluation into your loss function if you use this language, or into your optimization criteria. That, though, requires fast estimators or fast evaluators for those properties, because a lot of them do rely on the structure in the first place. But for example, I spent a good part of my career working on the thermal transport properties. Optimizing thermal conductivity is a problematic problem, because careful estimation of thermal conductivity takes orders of magnitude computational times in comparison with the structure evaluation itself. And so this is just unfeasible to include it here. There have been people who've done great work on developing fast estimators. You do need to involve a lot of material science and physics into this, but it is another possibility and another direction to go here. Let me make a very short survey of the tools, which is not even necessarily a survey of the tools per se, but what kind of global optimizers available out there. They don't come in any particular order here, and sometimes I do have some specific code. Sometimes there is different codes available for this. So I very roughly describe this as there are genetic algorithms that allow us to say something. There is simulated annealing type techniques, either Monte Carlos based or molecular dynamics. There's something called particle swarm, which in some sense may be similar to the simulated annealing, but trying to take advantage of the parallelizations available. What I call brute force is either something that looks for the possible arrangements of the atom on the grid or maybe random sampling of the things. So this is basically an attempt to cover the entire configuration space. And finally, there is a data-driven approaches, which were highlighted by this large language model, so something similar, which attempt to predict what is the structure of the material is going to be based on this composition by training on the large data set of existing models, which of course appear in the latest time. I'm not sure how exactly they perform at this point. We choose to work with a simulated annealing here for multiple reasons. Some of them is familiarity that I have with this type of techniques, so I feel reasonably comfortable working in this direction. Others is, at least in principle, there is some theorems which I would not dare to state because I'm not a mathematician, so I will not push that far. But there is at least some theorems which claim the convergence of the methods, and I will discuss a little bit about convergence, to what certainty we can argue that we actually found the lowest energy state. They are, of course, subject to the various sets of conditions, which is not entirely clear if they are fulfilled in our particular simulations or not. But at least there is at least something which tells us about this direction. And I will talk about practicalities as well later on, because in practice, all of that essentially is not fulfilled. We are basically limited by how many evaluations you can afford to make. The energy evaluators themselves, we are living in the world of relatively small systems as far as computations are concerned. They're still large enough for the global optimizers, but they are small enough in the sense that we can do ab initio calculation. I'm always using quotation marks in case there's quantum chemist in the audience, because they don't like the notion of the density functional theory as being an ab initio method, but that's discussion for another day. For a moment, we'll just say that they're reasonably accurate and they're slow. And when I say reasonably accurate, when we're talking about structures, density functional theory, by and large, I think everybody would reasonably admit will predict the properties of the structure with the accuracy of a few percent, which is of course great. The other option here is to use a classical potentials, and classical potentials always has been a problem up to a very recent past. They've been a problem because we, in complex chalcogenets, we have situations where we have 3 and 4 and 5 different elements, and that's traditionally been a problematic point for even the most advanced classical potentials. I spent some amount of time working closely with people fitting potentials, and every time I hear that 1 element we can do great, 2 elements we can do reasonably well, by the time you hit 3 elements or 4 elements, it's starting to be a question. Something which is extremely simplistic is not going to be transferable. Something which is very advanced will have problem predicting anything outside of the data set in any significant accuracy. That situation have changed somewhat recently with the advent of the data-driven approaches. I will discuss a little bit application of the CHGNet neural network potential, which takes advantage of this data-driven things, and what my experience with that thing was. So we basically, we are focusing on DFT, but lately we switched to a combination between DFT and the CHGNet potential. So how are we going to attempt to reduce the dimensionality of the thing? Because for me, again, it's a kind of a key issue here. And one, we take the full advantage, or attempt to take a full advantage of crystallography or solid state physics, depending where you came from. We're going to force a particular space groups, and we're going to sample all the different space groups. So that achieves multiple things for us. Number one, it allows us to generate very diverse structures with which we're going to be working with. And number two, that automatically generates multiple starting points for our simulation. Of course, looking at different space group is also trivially parallelizable, so that allows to take full advantage of the computing infrastructure. In addition to the space group, one, of course, want to use the Wyckoff position to classify possible atoms positions in the system. And so basically what we're going to do is we're going to arrange our possible atoms and or rigid blocks, and about which I will say in a moment, in various combinations with respect to the Wyckoff positions that are possible in a given symmetry group. I will discuss what kind of issues that approach runs into in a little bit. Another way we're going to another way we're going to reduce the dimension is we're going to use this rigid block idea. And this idea here illustrated by the chemistry reaction that I have presented at the bottom here. It's called the metathesis reaction. I promise that's the only piece of chemistry I have. Just like in some of the physics talk, people say this is the only formula I have. Same for me, this is the only chemical reactions I have here. And what you see here is on the left, we have, maybe I can use, yes, I can use the mouse. So on the left here, we can see that I have complex halogenides, sodium, germanium, selenium compound. And it has this fairly complicated structure, as you can see, as is presented. And as we look at this, we can notice that germanium, selenium parts of this compound, they form this dumbbell-like structure. It is a dimer which forms by germanium-germanium bond with the selenium sticking out at its points. And the premise of the metathesis reaction is that this rigid block, this combination of atoms, actually transfers out and stays fixed in the resultant compound when we combine this with, in this case, ensalantanum, chlorine-free. And we can see that this rigid block stays intact. That does not change. And we do change the elements which we have inside. So we now have lanthanum contributing to the system, and it's now a part. In this particular case, it's going to be some disorder here. It's going to be partial occupancy. So that particular combination will cause a trouble. But the important portion, again, is that this germanium selenium piece is actually staying in one piece and not really changing its relative orientation of atoms. So we're going to treat this combination of atoms as a rigid block rather than as a molecule, if you will, rather than thinking about that as an individual collection of atoms. And that is going to save us on some degrees of freedom. In this particular case, for example, I have 8 atoms, which would nominally have roughly 24 degrees of freedom. I'm trading this in for 3 degrees of freedom associated with the motion of the rigid block and 3 degrees of freedom associated with rotations. So I hopefully achieve some reduction. Without the computation, as I will point out later, we do have a way to kind of keep in check whether this rigid block actually falls apart or not, meaning that our approach is not going to work for this particular combination, or also adjust the relative size of that thing, because obviously in different chemical environments, I expect this rigid block to not necessarily hold steady and be the same. So these are the two ideas that we're trying to implement here and to use to reduce the dimensionality in our systems. How widely applicable it is in complex halogenides. Here is the list of possible examples of the rigid blocks that for which some amount of chemistry have been described. So we have tetragonal rigid block right here. We have a double diamond of the type that I described. We have a tetragonal blocks with a shared corners. And the interesting piece about that, and this was actually motivated by some of the previous work, in beginning of 2000s, there was a series of works where people were looking at the possibility of taking the rigid blocks like this and combining them together via the corner sharing or edge sharing orientations. We would like to go there as well, because it's one of the modes how we can also keep the rigid block intact, but yet get some more interesting chemistries, but we didn't quite reach this point yet. So the next block, I can view it either as edge sharing tetrahedral units right here, or I can think about that an individual rigid block as well. And you can see other combinations, they go all the way up to the fairly complex structures that, again, can be kept intact, maybe kept intact without some chemical reaction. As I already mentioned, throughout the search for structures, the dimension of the block, their bond lengths will be optimized. So I'm not going to get stuck with a particular size, with the particular dimensions. And each one of the rigid blocks also have their particular point group symmetry associated with that. And this is now also nice because it will offer an additional reduction. The point group of that rigid block has to match the point group of the Wyckoff point at which I'm going to place this thing. Otherwise, this thing is not going to fit in there. And this is, of course, very nice because that allows a further reduction of the possibilities, which is, of course, quite important if I want to be able to predict reasonable structures. Convergence. By convergence, I understand the question of whether we actually, with any certainty, can tell that we found the lowest energy structure. Again, as I already mentioned, convergence theorems require logarithmically divergent time with the size of the system, which basically means that in the simulated annealing scenario, when you lower your temperature has to be lowered slow enough so that you would be sitting in the lowest attraction basin of your system. That should be a logarithmic decay in time due to the Boltzmann distribution, of course, that's typically used in simulated annealing type of scenario. The problem is that it takes too long, of course, and realistically, nobody can afford this kind of scenario. There is some potential, there is some work in the global optimization community when they're looking at the different sampling on the, so I'm going to use a Monte Carlo type simulated annealing in which the new structures are going to be predicted some distance away from the previous structure. And I can endow this search with some distribution function, which will tell me how far away from that first location I'm going to be. And there is a possibility to employ distributions with longer tails, which would encourage longer jumps for the possibility of exploration of the phase space, which claim better performance. This is something which I really much would like to exploit and explore in this context, but at this point, we cannot really tell if that's going to be beneficial or not. As I already mentioned, in practice, we are really limited by the execution time. So a typical simulation run for a given structure, by our experience with the hardware that we have and everything else, we typically can evaluate on the scale of the 10,000 structures. So this is our kind of a limit for the representation in a given space group. So this is our typical run, which will take us about a day or so to run. And if I want to sample a few different space groups, then one can correspondingly increase that number. And one other thing which is kind of important or useful in this context is if I manage to find a lowest energy state in a particular group, then I should be able to find the same lowest energy state in every subgroup of that group. There is, of course, 230 space groups available over there, and many of them are the subgroups of each other. And if I find the same structure as the lowest energy structure in every subgroup of a given group, then that gives me some degree of confidence that this is the lowest energy structure. It's only an indication, that's an additional piece of evidence that we can use, but nevertheless, it is also there, and we want to take an advantage of that. Some practicalities reasonably quickly. Initial structure play a key role, a very important role in this. We kind of have an idea about what the densities of those compounds are going to be. So this is where we're going to start from. We're going to enforce the minimum interatomic distance because we know that atoms cannot be very close to each other. We don't have hydrogen here or fluorine, so we can survive on putting pretty strict restrictions on that. And we're going to randomly place the atoms in the associated Wyckoff positions. For every given simulation run, we will pre-assign what atoms to which Wyckoff positions in the primitive cell are going to go. If the search is unsuccessful for the random structure this way, then we're going to decrease the density, increase the volume, because that will relax a condition on enforcing minimum interatomic distance, and we will attempt to initialize again until the process is performed, until we find the structure. And in the end, we will perform a local optimization from this point. This is something which kind of hard to include in the general discussion how the system is working, but one always have a tool of doing the local optimization from any given point. And what we're going to do in general throughout our simulation is periodically we're going to run a local optimization in order to mitigate a little bit maybe this effect of not be able to cool sufficiently slow. That's the point that I just made. We're going to do periodically perform local optimization in order to settle down our structures and see where we are. And that also allows us for checking if the rigid blocks actually fall apart or not. In all our experience so far, we had only one system where the rigid blocks started to fall apart on us. So we think it's reasonably applicable. And even in that particular system, it turns out to be an operator error. We were looking at the manganese compound and we did not include spin. And that is a big no-no. So once the spin was included, everything was well behaving, nothing was falling apart. So the cooling that we're using is, of course, much faster than logarithmic. And in the grand scheme of things, really, one might as well just keep effective temperature of the system in a sufficiently high value, so it just serves as a sampler of the phase space. One other important thing to point out is any symmetry restricted searches quite often result in local maximum rather than local minimum, or maybe the saddle point on your phase space. And so dynamical stability of your structures is important to assess. Fortunately, these days, calculating phonons on something which has 20, 30 atoms per primitive cell is not extremely difficult. So all the structures that I will report today pass that filter, and all of them have a stable phonon structure. I will not show phonon band structures because we don't really use them for anything useful other than one little piece. But this is to ensure that the structures are dynamically stable. Let me have an overview of the method. So this is kind of a big plot which shows what we have. So again, we start with a rigid body on a given composition, on a given compound. We do the symmetry analysis of the rigid body to identify its point group. All of that is automated at this point. Python libraries are great in this regard. They are very useful and very helpful. And then we start to count how many different possibilities, how many different permutations, how many different combinations we have of placing atoms that we have in our system, usually metallic atoms, and rigid bodies into a particular setting of the particular space group. And for some space group, as we will see in a moment, there is a lot of possible combinations that it isn't practical, and this is one of the sort of stumbling blocks on this direction. So we will limit ourselves to some max number to be practical, and within these groups, within these selected space groups, we will run all possible combinations of the arrangements of atoms and rigid blocks among the Wyckoff positions. So that will generate an initial random structure in this place. The structure will be deluxe, just as I described, and launch into simulated annealing simulation, in which case it's going to be a Monte Carlo simulation in which we're going to use metropolis acceptance as a criteria for accept or not accept a new structure. We will periodically do relaxation to ensure that the rigid blocks do not fall apart and everything checks out, and that will produce the candidate structures, which we then will record and keep track of what the 10 lowest structures in a given thing is. That will follow post-processing, in which case we're going to look at what are the possible candidate structures, what is the relationship between them in terms of group-subgroup relationship, and possibly, not possibly, but looking at the phonons at the most promising structures. So this is kind of the overall setup. This is the example of the system that you're going to look first. Again, this is the test of the method rather than prediction at this point. So there is a well-known results for what the ground state and metastable structures are. I will show them towards the end of the discussion on the system. Here I have a tetrahedral block, which is shown on the picture here. The phosphorus atom is in the middle and the sulfur atom are spreading around. So one can make a primitive count and convince themselves that 15 degrees of freedom being reduced to 6 in this process. We're going to limit this to up to 3 stoichiometric units per cell, and this limit is simply to limit the time spent on the first principle calculation. So again, this limit is only comes from your computational abilities available to you rather than anything else. There is nothing fundamental about that. And for the larger systems, therefore, for the 3 stoichiometric unit, if you happen to be in the group P1, which doesn't put any additional constraints or restrictions, then we're going to go from 72 to 45 degrees of freedom, which is, again, one can argue is not a terrible degree of reduction, but again, this thing blows up exponentially and even worse, so that is reasonably useful. This plot represents here a number of possible combinations of arrangements of the atoms and rigid blocks among different Wyckoff positions in a given space group. Again, this plot generated effectively automatically. Notice the log scale on the y-axis. So there, and the ones that are terminating at 1,000 is basically when we lost patience and said we're no longer going to count. There are so many different combinations that we're not really going to run this anyways, because it would imply that I need to run basically 1,000 different simulation units with different combinations. The issue is basically in the fact that some space groups have a large number of the Wyckoff positions, special Wyckoff positions, which might not have any movement associated with them. That might be a special point in the brilliant zone, and there might be, for example, 12 or something on that scale number of the Wyckoff position. If I have 6 metal ions that I can put into those Wyckoff positions, this is the number of possible combinations I can sort them out with, and so that will be a challenge. And this is where I will have a lot of these different combinations. So one problem which we didn't solve here, which we would like to solve, is there a way to continuously transfer from one set of Wyckoff positions to another set of Wyckoff positions, so that I would still have an opportunity to sample any particular group? And that's the problem which we tried to tackle, but we are unsuccessful so far. So what we're going to say is that anything which has less than 20 possible combinations is the space group we're going to sample. So the space group that are shown in yellow, these are the ones in which we're going to run the simulations. All the blue ones are going to be abandoned. And again, one may argue that as I go from left to right here, this is the number of the space group, then I'm going to increase in degree of increase in symmetry of the system. As I go to the large symmetry in the system, to the higher symmetry of the system, I will have less degrees of freedom. But at least in principle, I still should be able to find any structures in the space group if I'm looking at the space group P1, which of course doesn't have any symmetry. Of course, in that case, I don't get any benefit of symmetry reduction, which means that I might wander in the phase space forever and don't find anything useful. So we run these calculations. These are the results, and these are the results for the lowest energy system, lowest energy structures found in every space group that were considered. In this case, you can see that there is still a good number of blue dots. So in this case, we still have reasonable number of space group in which the simulations was performed. And you can see that the red dots are indicating the lowest energy that we have found. In this particular system, the lowest energy, so-called gamma phase of lithium PS4, lithium-free PS4, crystallizes in the group 31. And you can see that I also have 3 other groups where I found the same structure. And these 3 other groups is group P1, which is of course subgroup of every group. And the other 2 is group number 4 and group number 7, both of which are subgroups of 31. So this idea that I can find a given lowest energy structure in every subgroup of a given group is allowing me for consistency check, and it gives me some degree of confidence that I have found what I wanted to find. This is the plot that shows all possible structures in addition to various metastable structures that we found, and it also shows the representation of those things in the ball and stick model. You can see that there is a pretty wide variety of different arrangements of things, and you can see that we sample and find various other structures. Let me talk a little bit about agreement with the experiment here, because as I mentioned, gamma phase is the known ground state of the system. The phase which is most interesting for the application is the alpha phase. And as you could notice, we didn't find neither alpha nor beta phase. The reason we didn't do so is because both of those phases feature disorder. In both of those phases, we have some degree of vacancies, which are randomly distributed throughout the system. And the energetics of those phases is not our work. This is the work out of the Seders group, which carefully looked at the various computations. So in this work, they only try to estimate what is the relative energy of these phases. They didn't do anything else in this. So this is a separate paper. So this is estimating the energy of those structures is much more difficult proposition. And this is precisely what I was saying when I said that disorder is something which we really like to be able to invoke here, but it is very challenging to do so. Otherwise, gamma phase is the lowest energy phase, and that's precisely what we found. We can look at the performance a little bit. What's shown here is the evolution of the lowest energy structures shown in red, and other dots is other considered structures. This is not terribly informative graph. I wanted to show one good case, and good case is shown on the right here, where you can see that after about the number here indicate really the count of the local optimizations. By the time we got to the 20th local optimization or so, which means that we consider about 100 energy evaluations at this point, 1,000 energy evaluations, excuse me, we already found the lowest energy structure. So again, something which has relatively low degree of dimensionality. This is where, this is how fast you're going to find it. The case on the left is kind of one of the worst cases that we have found. In these worst cases, we only found the lowest energy state by the time we hit about 30,000 evaluations. So if you are unlucky, this is how far one would need to go. Again, this is in one particular space group. And so again, this is the question of how certain are we that we have a convergence of our system. Next, we looked at the situation when we don't have a single lithium, but we have a lithium combined with another metal. This is a standard idea that one can use in order to develop a different chemistry, because if you substitute it for the lithium, which has for the metal that have different oxidation state, then one has a potentially to generate a number of vacancies in the structure. And these vacancies are, of course, hopefully would be beneficial for the ionic conductivity, for example. This is our main driver here. So I'm looking at the two different metals, zinc and manganese, and in this case, there is a drastic increase in the number of the combinations to an extent that I really cannot do what I have done for the lithium PS4, which is run somewhere on the scale of 60 or 70 different space groups. In this case, we limit our simulations in 3 different groups and look up to 4 stoichiometric units. Of course, the structures that we found as a result of the simulations can be in the higher group setting by the virtue of the fact that symmetry will come into play when the lowest energy system will be found. And indeed, we find these different candidate phases. And in this particular case, for the case of zinc, there is also known lowest energy structure. It is indeed in group I4, bar 4, group 82. And this is indeed also what we have found as well, in addition to some metastable phases. So again, it is a reasonable success in the sense that we were able to find the experimental structure here. In the case of the manganese, life is a little bit more interesting. We found that the same type of structure as in the case of zinc, is the lowest energy structure according to our calculation. Experiments, however, have found it's crystallizing in the group 62. And we, of course, can take the experimental data and we can calculate the energy of that structure. And we found that the energy of that structure is higher than the energy of our predicted structure. So it is possible that there is kinetics comes into play. It is possible that as we elevate the temperature, then situation is different. Though in this particular case, we're pretty confident that it's not the case because we did also calculation of the free energy, including the phonon subsystem, and we still find that this structure that we found is the lower energy. But it is also possible that whichever method is used to synthesize this structure does not allow to go to the true ground state. So that's something which we have to run with our experimental collaborators and see if that makes any sense. The other system we looked at looks at this sodium germanium selenium system, and that has a larger rigid block. It's a rigid block that reduces 24 degrees of freedom to 6. It has these features shown here. Again, the same kind of idea that we're going to run. I'm not going to run through all the details. I'll show the results here, because this is also the situation where we found a different structure from the one which was found experimentally. Experimentally, the system was considered some long time ago. There is a single paper which presents XRD and shows the solved structure, and it is claimed to be crystallizing in space group 14. We actually found that structure as well throughout our simulation, but we also found a structure which is significantly lower in energy as well. So we have run a whole bunch of simulations trying to see what kind of different properties this have. It has more interesting properties or not. And I think, honestly, in the grand scheme of things, it doesn't have anything more particularly interesting, but it is a significantly different structure. In this particular case, however, we do have a little bit of the explanation why it might be so that experiments found the different structure, because we can add the phonon energy to the system to calculate the free energy of the system, which now includes phonons contributions. And if we do so, we see that the free energy does crosses over at about 900 degree Kelvin. And the sintering temperature for many of these compounds is somewhere in this range. So it is entirely feasible that when the solid state reaction was taking place at this elevated temperature, the system basically stayed in that lower state once it was annealed down to the lower temperature. Again, in the case of the manganese, this is not quite the case. In the manganese, these lines never cross, and so it's a good question if the different structure is still out there. We run the comparison with the genetic algorithm in order to see where we stand or how well it performs, and this is kind of a summary of what we have. So we set up the spec calculation on the same systems. Lowest energy structures were visited roughly after the same number of energy evaluations. I say roughly because depending on where you start, all your initial starting points are random starting points, so you never really know. We run a few different evaluations, and again, the scale of the place where it happens is about the same. The important difference that we found is that Uspech calculation not being restricted to a particular space group in the first place, typically finds the lowest energy structure and then hangs around that lowest energy structure and have a little bit of a difficulty finding various metastable structures. That comparison is not entirely fair because we are not an expert in the genetic algorithm methods, and it is entirely possible that you can tweak the algorithm so that it would look for the metastable states. But nevertheless, we kind of see that we can fairly confidently find metastable structures in addition to the stable ones, which I think would be the key to look at the various disorder states. And so this is sort of a key result of the comparison here. The last thing which I want to point out, really, and I'm getting close to time. Oh, excellent, yeah, exactly. And the last thing which I want to point out here is we came across this neural network set of potentials. I was originally fairly skeptical that it might work, but what you see on the plot here is a comparison between DFT methods, and I know it's typically tend to show as a neutral plot. That's a different type of plot, but we decided to show it this way. But nevertheless, this neutral network potential has a very decent accuracy in predicting the energies of our system. It's not ideal. It's not ideal in the sense that when we compare in small energy differences between our candidate structures, we do not find the same order of structures as in the DFT calculations. But there we are talking about MEV differences per atom in that case. When we are talking about larger differences while we sampling the phase space, then CHGNet is more than adequate in order to tell us, is that worth looking here or it's absolutely not worth looking here in that particular region of space. And so our current implementation of the code invokes, when we are running the simulated annealing, it uses CHGNet as an energy evaluator. And when we go into the local optimizations, that's why we employ the DFT as a more accurate technique to run through this. CHGNet is not as fast as the past classical potentials. It lies somewhere in between as far as its simulation time. And so it is still not ideal, but maybe they will improve. Let me conclude with this. We have successfully implemented a symmetry-restricted rigid block DFT-based crystal structure prediction approach. For the test systems that we have considered, we found all the lowest energy, all the observed experimental structures, and in some cases we predicted additional one which might be even lower in energy in accord to DFT. So one may argue if that's a DFT problem, that's not a global optimizer problem, right? If the DFT fails to predict the correct order of energies. We successfully found many metastable structure candidates, which I hold as a key to consider disorder structures. So this is something which we will be thinking about in the future. The Python version of that is available. Chi did a great work of organizing everything. He even had to fix some of the well-known Python packages out there because they contain bugs, as it turns out. And as I already mentioned multiple times, disorder and optimizing against other properties is what we would like to pursue in the future here. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Aleksandr. Please thank Aleksandr for the insightful talk, physically or virtually. Let me stop recording.